So far we have seen then that um, with the no interaction model, which means that there is no interaction between vibration and rotation, we have considered the case of the real rotator, which means that there is a centrifuge distortion D. However, experimentally speaking, actually we can notice that the spacing between the lines of the ridge band actually gets smaller and is different from the spacing between the lines in the pool band. I recall that the lines in the pool band and the lines in the ridge band correspond to spectral lines from rotational transitions, and supposedly B, which is the spectral term of the rotation, should be constant. However, experimentally speaking, this is not the case. And in fact, this behavior comes from the fact that the first approximation of the non-interaction between the vibration and rotation of a molecule is not correct. In fact, there is an interaction. Why? Because when the high vibrational energies are reached, so if the molecule is vibrating at higher energies of vibration, the amplitude increases differently between the different levels, which would lead to a different value of B, meaning that the rich band and the poor band will see a different spacing between their lines due to the fact that the B constant of the rotational energy would not be the same for the same levels of energy, or vibration energy. So we call that B prime for the level 0 and B second for level 1. And our goal is to see how these different two values would interfere in the expressions and how we can calculate them from the spectra. So now we are no longer in the first approximation case, so we are in the actually real case where we do have an interaction between the rotation and the vibration of the molecule. And in this case, we consider first a negligible value of the distortion, meaning that we consider that the rotator is rigid, but with interaction between the two modes of vibration and rotation. So basically, when we do obviously you know that we are going from one level of vibration V to another level of vibration, higher level of vibration. So from V equals 0 to V equals 1. But since the value of B is expected to be different at these two levels of vibrations, so if the molecule is in these levels of vibration, then its rotational spectral term in these levels would be different. Then when we look into the delta J plus 1 transitions, so basically it's the ridge band, the delta F would actually take this form where we have B second and B prime, B second being the rotational spectral term when the molecule is at the energy level V equal 1, and B prime is the same spectral term but when the energy level is at V equals 0. In the first approximation, these two values were the same. And same thing happens for delta J equal minus 1, and we got to this expression between B second and B prime for the transition of in terms of rotational energies. Now again, what interests us is the spectral lines on the spectrum that we get. And the spectrum that we get is basically for vibration and rotation. So we are going to look into the transition corresponding to delta J equal -1, obviously always delta V equal 1, so we are moving from one level of energy of vibration to another. But here we are taking the case where the transitions sorry satisfy delta J equal -1. For delta J equal -1, if you recall well, this cannot happen unless the first level of energy of rotation for the first level of vibration, so the seat in which you actually are in the row in the class, the initial row, should be J equal 1. So we go from J equal 1 to J equal 0, and then we have delta J equal -1. And when we do this delta G plus delta F, we actually get into this expression of the spectral line. So that's the wave number of the spectral line for the pool bend. Now, if we want to look, and that's what interests us, is the first line in the spectral bend, the pool bend. Well, this, as we said, corresponds for J equal 1. So if you put J equal 1 here, we get that the first line, spectral line, will show up on a wave number in the pole bend equal to omega 0 minus 2b prime. Remember that in the first approximation that was omega 0 minus 2b. Now same thing for delta J equal +1. Now we go from J equals 0 at the start, because we can go to the second level of vibration of energy with J equal 1. So from 0 to 1, that's delta J equal +1, that's fine. Then we get into this expression. What interests us is the first line on the rich bend side, and this starts from J equals 0. So if you put J equals 0 here, you will notice that it's omega 0 plus 2b second. So again, for the first approximation, that was omega 0 plus 2b. So now we have omega 0 minus 2b prime on the left side and omega 0 plus 2b second on the right side of the gap for the first lines. So this gap would be the difference between this first poor bend line and this first rich bend line. And if you do the difference between them, you will get into 2b prime plus 2b second. Remember, again, I always recall it, for the case of the first approximation that we started with, where actually there was no interaction and that b was constant, then this difference was equal to 4b. Now the question is, well, if we do have b prime and b second, if the spectral terms are different for different levels of vibrational energy, how can we get them? Well, the procedure is, it's easy to say, it needs to be seen and represented in a neat way again. It says that, well, remember that we have b prime for level 0, v equals 0, and b second for level v equal 1. And then the lines on the spectra correspond to transitions for rotational states while we are going from v equals 0 to v equal 1. And since we have this rules of delta J equal -1 and delta J equal +1, then there will be cases where on the side of the pole bend there's a transition starting from a certain level of rotational energy, and on the left side, which is the pole bend, there should be also another transition that starts from the same level of energy in V0. But because delta J must be -1 compared to the first case, then this level would go to a different value. So if the upper levels of the transition are the same in the case of transition in R and P, then the difference between their spectral wave numbers only depends on the properties of the lower level state, and vice versa. Now this is going to be complicated if you want to read it or hear it like that. Let's see it. So again, I recall we are in the real rotator, so there is interaction. There is interaction means the B prime or the B values for different vibrational levels are not the same. Now again, you see you have the first vibrational level V equals 0 and the second vibrational level V equal 1. And because we are considering this interaction model, so the real rotator model, we have put that for all these lines the spectral term should be B prime, and for all these lines the spectral term should be B second, because B is different. Now notice the dashed lines. You can notice here that the two lines, one of the side on the side of the poor band and one on the side of the rich band, they both land in the transition on the same final level, which is in this case J equal 1, right? So obviously the difference between them, if I take this spectral line from the graph and the other spectral line and I seek the difference between them, then this will be the difference between these two levels. And notice, this one goes from J equals 0 to J equal 1, so delta J equal plus 1, and this one goes from J equal 2 to J equal 1, so that's actually delta J equal minus 1. And so what we will do, this is very, how to say, this is very broad. We will see it with actual numbers, but the difference between a rich level of energy and a poor level of energy, or if you want a rich line, spectral line, minus the wave number of a poor spectral line, both of them ending at the same level, higher level, so the final level, then the delta between their rotational differences corresponds to this, and it's going to be 4B prime J plus half. Why? Because you see, since they end up on the same level of rotational energy where the spectral term was B second, and when we make the difference, if we make the difference, it's going to just show up between these two rotational energies, which correspond to a spectral term B prime. And the other way around, if actually we take two lines that end up or start, if you want, in absorption, they start from the same level. So look at this. I mean, there are several ones. You can take this one and this one. They both start from J equal 1, but they end at two different J's. This blue one goes from J equal 1 to J equal 2, and this one goes from J equal 1 to J equal 0 to satisfy delta J minus 1, and here to satisfy delta J equal plus 1. So now if I take the spectral line corresponding to this transition minus the spectral line corresponding to this transition, it's going just to give me this difference. And this difference actually is in the case where, or for the level V equal 1, where the spectral term of rotation is B second. And this gives us this relationship. Now the idea is we can actually introduce to that a centrifuge correction. So we introduce a centrifuge correction which we consider to be constant, because you will see that we can also consider it not to be constant. If the correction of the distortion is considered constant, but that there is an interaction, then we have B prime and B second for the two levels of vibrational energy, the consecutive ones, but the D is the same for both cases, and this adds up this term of correction with the distortion correction that you have seen before. This one for the delta J equal plus 1, and this one for delta J equal minus 1. Now, just to make things even more complicated and to get our brains really lost, well, there is an additional situation where we have a real rotator, so we are no longer in the first approximation. We do have interaction between modes, so the B prime and B second are different, And also there's a distortion correction, but even this distortion correction will actually depend on which level of energy we are on the vibration side, which means that there will be d prime and d second also. So yeah, doing the calculations gives us these expressions. Well, I mean, honestly, no one would be asking to memorize these expressions or to calculate them. It's silly. But you should understand what they mean. Okay, so we just added the correction, but we added the correction for each level of vibration, of rotation, differently, because one level has B prime and D prime, and the other level has B second and D second. Now again, same idea. If I want to find the difference, so if they end up at the same level, and the difference is here, so it's going to be containing B prime and D prime, which is the case in here, where they end up at the same higher state, and vice versa when they start at the same lower state. The difference between the spectral lines would be depending on B second and D second. In this case, if we take the gap, so the first line here and the first line here, you can just calculate them from here. We get into this relation. So the gap now is 2b prime minus 2d prime plus 2b minus 2d second. This should be b second here. Now, that's all nice, probably complicated, probably a lot of formulas and confusing. So how are we going to use this? That's the important part. I mean, I would appreciate that you understand the physics, that you understand that these effects can be taken into account. But what imports me is how we can use that. Well, this is an experimental spectrum for a rotational vibrational case, where you see clearly the two bands and you see the gap in between them, and you see that the gaps in here are not actually the same as in here. So immediately one can tell that we are in a case where it's considered as a real rotator, so there is interaction between modes of vibration and rotation because the spacings are not the same. 1, 2. We have the rich band on this side and the poor band on that side. Now, how can we determine B prime, which is corresponding to P for V equals 0, so the first level of energy of vibration, and how we can determine B second? So as we said in here, look, say we are in this situation, so we have to see the lines that end up at the same level, and then we get from that the B prime, and then we have to see the lines that end up at the start up at the same level of V vibration. Then the difference between them will just be depending on B second. Now, I think we are neglecting in this case the centrifuge correction. So we're just taking the interaction between them, and what we will do. So we give you actually, and you will see in the problems, so we give you basically a hint or directly the spectral lines values, so the wave numbers of the spectral lines that appear up in here. And in this case we said that, well, the spectral line appearing at this wave number, so on the graph, actually correspond to the transition from V equals 0, J equals 0 to V equal 1, J prime equal 1. So this is obviously delta J, final minus initial, is plus 1, so that's in the rich band. Same thing, another spectral line, delta 2 to 2590, appears at V equal, transition from V equals 0, J equal 1 to V prime, actually it should be equal 1, to J prime equal 2. Okay? Great. Now what? Same thing for the levels where we start from V equals 0 to V equal 1, obviously, but then delta J goes from J equal 1 to J prime equal 0, so that's minus 1, and here from J equal 2 to J prime equal 1, minus 1. Now if you want to get to B prime, so B prime is for the levels of rotation that correspond to the vibrational level V equals 0, the difference between them. So we should look into the states that end up so that they have the same higher states or final states. So between these, so obviously we take one from the rich band and one from the poor band, and we look that this first one, J prime equal 1, so the final state J prime equal 1, and here is also J prime equal 1. So these two lines, this one and this one, they end at the same level of rotation at V equal 1. So if we take the difference between them, this would be the difference between the two positions of the starting levels of vibration of rotation on the V equals 0 level. So if you do the difference between them, this will give us 4B prime J plus half. So we have the numbers and we get to B prime. Why we have taken J? Because basically J is the one that we started with. So we started with what basically? So that's the common one, I mean. So that's the common one. So the common one between these two is 1. So if you put 1, it's 3 over 2 times 4, it's 3 times 2, it's 6B prime. And we get to B prime. Now if you want to get to B second, then we have to take the lines or the transitions that start from the same level of rotational energy, and they have different final levels of energies. And between these two cases, we look into what is similar in here. Well, this one starts from 1, and this one starts from 1. So the difference between them, if we make the difference between them, this will be 4B second now, J plus half. And J is the one that is common between them, which is also 1. So this is also going to give us 6B second. And so we have B second and B prime. Now he's asking also here to calculate the force constant. Now if you recall in the vibrational case, the force constant is given by the square root of K over mu, or 1 over 2 pi square root K over mu. But this means that we need to actually just have the information on the on this frequency, which comes from the vibration. Then in fact here we use the central point, the central line in the gap. So the central gap, if you want, corresponds to a transition that is not allowed. So this is why it's a gap, because it's absent. So the distance, if you want, between the the first line in the poor band was equal to, look, omega omega 0 minus 2B prime. So if I come back here, so the spectral line for the first poor line in the poor band is omega 0 minus 2B. Now we put nu 0 because we divided by C. So from that we have B prime now, and we have the value of this first spectral line. Now the question is, which one is the first spectral line on the poor band? Well, that's the one that starts from J equal 1. So that's this one. Sorry, for the poor band, that's this one. Okay? Plus 2B prime, so we have B prime, and we get this spectral line, or this one, this frequency basically, or wave number, is 1 over 2 pi radical K over mu, which is the frequency, over C. This gives the wave number. Now there is an energy, there is a relation between B prime and B second, knowing that B prime is B for V equals 0 and B second for V equal 1. Now, I really don't necessarily care about this. What I really care about is this relation. So B for a given V is B minus alpha. B is the constant one. So what imports us, if you want, or that's more like V plus 1 and V. So alpha, which is a constant of a small value, it measures the interaction between the rotation and vibration, if you want. So if we take delta BV, we will get into alpha A. So if you have B prime for V equals 0 and B second for V equal 1, we have calculated them. You make the difference between them in terms of absolute values, and you get to the constant that measures the interaction between the two modes, rotational energy and vibrational motion. Same thing for the D's, but here we don't really have an expression, so that's more, if you want, like general information. And finally, very quickly, something about the isotopic effect. So here we have a natural mixture of D35Cl and D37Cl, and they show up like this in terms of rich band and poor band. Now clearly, when you look at this, you can tell that the more abundant isotope is the D35Cl because intensities are much higher. But the thing is, since the vibrational, the rotational term is a function of 1 over mu, then if I take B for the one of the isotope over B of the second isotope, it's just the inverse order of ratio of their reduced masses. Okay, so if I have one, or if I have this ratio and I have one of them, I can take the second one. And for the vibration, it's the omega E, which is, if you want, should show up in the middle of the gap, is a function of 1 over radical mu. So if we take the ratio between them for the two isotopes, it's going to be the radical also now of the inverse mu over mu I. Well, in conclusion, this this chapter really requires us to do something like this. Just give me the time that this opens. I will just say it now. In the very simple approximation, the two motions just add up, so there's no interaction between them. We actually go from one level of V to a higher level of V corresponding to delta V equal plus 1. And between these levels of vibration, we can do jumps in rotational levels, but respecting the case either delta J equal plus 1, and this will give us a rich band lines, or band of lines, or branch of lines, and delta J equal minus 1 gives us the poor side of the band, which is the poor, delta J equal minus 1, this is the poor branch of spectral lines. However, to make things a little bit clearer, let's try to summarize things this way. So the biggest model is rotation, vibration, right? Great. Now, we have seen that there are two cases. There is the case of the first approximation, excuse me for the writing, but I can do nothing about it. The first approximation, and the first approximation considers that there is no interference, no interaction, they are separate totally, no interaction between the two motions. Motion of rotation, well, my handwriting is perfect. You can consider me as a medical doctor, and the vibrational motion. So there is no interaction between them. That's the first approximation. And there is the second approximation that I will put with a different color. Well, actually not approximation, that's a simple, that's the real case. Let's call it the real rotator. And this means, yes, there is interaction. There is interaction. All along, interaction between the two modes. Which means that if the vibrational energy changes, this will affect the rotational levels. Now, in the first approximation, we have seen that we have also two cases. We have the case of the rigid rotator and the case of the non-rigid rotator. Well, in the rigid rotator, we know that B is same everywhere, and that D is practically zero, so there is no centrifuge correction. While for the non-rigid rotator, we still say that B is the same. Why? Because basically, and I will just show you this, B remains the same for the two bends, and this because B is the same because of this reason, because there is no interaction. So this is equivalent to say that B is the same. However, in the case of the non-rigid rotator, D is different than zero, but it's small. Right. Now, for the case of the real rotator, so where there is an interaction, we also take the case of rigid rotator. In the rigid rotator here, B prime for V equals 0. So the spectral rotational term now changes depending on the vibrational energy. Why? Because there is interaction between them. Different than B second, which correspond to all rotational levels included in the vibrational level V equal 1. And again, here D is considered 0. So D considered 0 comes from the rigid rotator, and this comes from the real interaction. And the second case, the non-rigid rotator, we also identify two small cases here, just to make things even more complicated. We consider that D, well, excuse me, let me put it differently. Still, because we have interaction, still in this case, it's the same as in here. So let me just copy that instead of wasting my time writing it again. Voilà. So even in the non-rigid case here, B still different. Why? Because of, again, because of the fact that there is interaction. However, in rigid rotator, we consider D to be actually negligible. In the non-rigid rotator, D is not negligible, but we identify two small cases also, as I said, just to make things even more funny. So we consider where D is different than 0, but constant, which means that for the rich band and the poor band, we consider D, but we take the same D. While here, D is also different than 0 because it's a non-rigid rotator, but we have D prime for V equals 0, for the level V equals 0. And this is not a prime, this is more like a dust, so I will D prime, which is different from D second, that corresponds to V equal 1. Okay, so this is, if you want, the diagram of the whole plan of the slides. So we have been moving from this first to this, then to this, and then we move totally to the case of there is interaction, so B's become different, but even in this case we've taken rigid rotator, so we neglected D, and in non-rigid rotator we also complicated our life with two possible cases. D is not negligible but is constant, and here D is not negligible but is different. That's all. That's the plan of this entire chapter. It's actually quite easy, so I will show you this in the slides, but I know from experience that this diagram, perhaps for those who try to follow up the lecture, would probably provide you with a nice summary of the whole ideas that kept going on and on and on. Okay, well, thank you for watching.